Hi, I am Shivji Kumar Jha. I am going to talk about streaming and structured data streaming at that. You can reach me out on LinkedIn, or you can talk to me on Twitter after the talk if you want to discuss something. Pretty open to that. And I hope you're really having fun with streaming, because it's the last day. I'll keep the talk a little bit light, but if you want to drop a question or you want to generally say a hi, please reach out to me over LinkedIn and Twitter. So a bit about me. I am a senior member of technical staff at Nutanix. My work primarily revolves around platform engineering, and recently I've been working on databases. I used to work at MySQL in the beginning. I worked on service-oriented architecture, where I've worked on microservices design, implementation, and all of that, infrastructure. And lately, I have been working on streaming technologies for last couple of years, and it's been mostly based on Apache Pulsar and the ecosystem around it. I love working on distributed data systems, and I find open source software and very sort of helpful. They help me learn as well as adapt them to use my use cases. And I have myself done contributions in Apache Pulsar with code, with documentation, with testing, all of that. And then I used to work for MySQL, so a lot of my code is there in MySQL as well. In this presentation, we will look at why schema. We will look at how, where we will see what's the different ways of putting structure on top of your data. We will look at popular formats, what are the different choices, the trade-offs between them, like what's good with one and what's bad with it. Then the next one, what's good with it, what's bad with it. And then we will look at some examples, and then we'll see some learnings that we've had over the years. For why, we will look at a little bit of history to see how over the last few decades, like 4 or 5 decades, we have evolved, and it does point towards something where it is pretty clear that having abstractions and forcing structures has been something that has helped adoption. So it all started around 1960s, where you used to use flat files to store data. Obviously, with flat files, the problem is how do you find data? And if you can't find it optimally, then reading is going to take time. Writing in any form, like new data or an update or a delete, is going to need you to go find the file and then perform these operations. So it's all going to be slower. Because we needed more structure, we went for hierarchical databases, where there is a directory sort of structure on top of data to organize it. And that's because we needed structure to find things quickly. In 1980s, we had this nice thing where we started using relational algebra, and on top of it, those concepts came to databases, and we had SQL databases, or relational databases as they are known. This has a high-level language like SQL, and then there are abstractions like tables and columns, data types, all of those. And of course, even since 1980s, it's still in adoption now in 2021. So pretty much 40 years, and then you have to acknowledge that in certain cases, relational databases or SQL databases have been really a thing of choice. Now around 2004, we had this huge revolution where we had a lot of NoSQL databases. Kind of funny that the name itself, NoSQL, is what it says it is not, but it was a jab at the SQL databases. So the idea behind NoSQL databases was that you can trade off some structure. We should not force as much structure, and we should trade off some asset properties, some structure that tables and columns put. We can get away with some of them, and then we can gain scale and availability for that. But then the interesting thing is that around 2010s again, we've had distributed SQL databases like Yugabyte, like Cockroach DB, and they're again trying to do the best of both these worlds, relational databases and NoSQL databases, where they provide distribution of data as part of the server. So they cater to your scale needs, and at the same time, they still support your asset properties. They still support your tables and structures and all of that. So you see, tables and columns and primitive data types and all of that are really strong structures, and these have stood the test of time. If you look at the streaming world itself and the history of it, Kafka was built inside LinkedIn, and then it became an open source database, open source streaming platform, and then it became Apache software. Then came Pulsar almost sort of 5 years later. Yahoo had some use cases where they wanted some good scale, one cluster for queues and streams, as well as a lot of good things about enterprise readiness. So they went ahead and made Pulsar for that. And Yahoo has made some nice distributed data systems, like Zookeeper comes from Yahoo as well. Bookkeeper came out of there as well. So Yahoo again built the new generation of streaming platform, and then it came to open source, and now it is an Apache project for almost last 3 years now. So if you look at the evolution, what does history tell us, right? We used to, even if you look at the organization of data inside a computer system, we have bits, but then we went ahead and made a higher level abstraction with bytes. Then we said we will use primitive databases, like integer is a combination of, let's say, on a given machine, 4 bytes or 8 bytes. And then we said we will use object-oriented databases. So we will have objects which have a lot of attributes of primitive data types. And we are now trying to use object-oriented languages to model our real world things as objects. So you see, there also, there is abstraction and forced abstraction on top of which the apps are built. If you look at the history that we just discussed, there were SQL databases in 1960s, then NoSQL databases in 2004 and later, and now in 2010s, we had distributed SQL databases. So SQL has very strict schema, actually. Evolution is difficult because alter tables and all can take a lot of time doing online. But people still want all that abstraction of schema and enforcing schema, so the apps can be forced to follow those schema when they produce or consume. The upgrade paths are easier. And if you look at the streaming world itself, we had Kafka, and now sort of 4 or 5 years later we had Pulsar. Both of them started with streaming just bytes, and then they later came up with the support for schema registry, which has all these constructs similar to the tables and columns in the relational database world. You want to, in my opinion, use schema as much as you can. There are, of course, certain use cases where you want flexibility. Of course, that comes at a cost. We will discuss the trade-offs, and we will look at schema-less world, and with schema, as far as schema is concerned, what are the different choices and all of that. But if you have to make an error on one side, I would say maybe have schema. A lot of times I have felt that in our industry, we are just a bit lazy defining the schema upfront. So we go with schema-lessness, but I would say it is worth giving it a good thought. We will look at schema a little bit, and then we will look at Apache Pulsar's constructs. Of course, Kafka's are similar as well. So pretty much the same concepts apply on Kafka side as well. But we will stick to Pulsar for the example codes, just because Apache Pulsar is something that I have been using recently. So first of all, we will look at a typical PubSub. A typical PubSub, you will have a producing app and you will have a consuming app. You have a producer library that is typically provided by the platform itself. It could be Kafka. This could be Pulsar. They both have their own client libraries, which have producer as well as consumer. You embed this client inside the app to produce, and the same client is embedded inside the consumer app to consume the data. But when you design your schema, you also have to make sure that going ahead in future, you will have a lot of producers, right? And then you will also have a lot of consumers. So when you talk of schema, your schema, if you want to change your schema, as in you want to add fields, you want to delete fields and all, you have to see that you have to do it in a way that doing it across all the producers and consumers should not be a pain. And if you go that way, like what you get in return is something that you should think of. Schema is nothing but encoder plus decoder. When we say encoder, you have an employee record. You can only store bytes in the computer system. So you put down an encoder, which will encode the employee record to make it bytes. And along with storing the bytes, you have to also store some hint about the schema. Either you keep the schema along with the bytes, or you can maybe keep a schema ID or something, and maybe you have a remote server, which given the ID can give you the schema back. And using the bytes and the schema that we talked of, we can pass it on to the decoder to give us back the employee code that we talked of. It is also something that is called serialization and deserialization. Encoder is your serialization and decoder is your deserialization. Now, when we talk of encoding and decoding, right? So producing schema or consuming data that has been encoded with a schema, we have three choices, right? Regarding the placement of encoder and decoder. So choice number one is you can put the encoder in all the producing apps, right? And you can put the decoder in all the consuming apps. Choice number two is that you can put it in the producer library, the decoder will be in the consumer library. The code is now abstracted out. The code is not split across your producers and consumers, but this producer code base still lives inside the producer apps server. So when you have to evolve your schema, once again, you have to now decide how do you go upgrading that across all your producer apps. How do you go upgrading the schema across all your consumer apps? And if you upgrade, in what order will you upgrade? Will you go upgrade your producers first, or will you go upgrade your consumers first? Will you upgrade all your producers first and then all your consumers? Or will you upgrade some of your producers and then some of your consumers? Like you have to decide what will be your upgrade path. And the choice number three is that instead of putting encoder here and decoder here, or in the second choice here and here, you actually put it on top of the streaming platform itself. And Kafka and Pulsar, which are really the most adopted open source streaming platforms, they both support encoder, decoder as part of their schema registry out of the box. All the constructs are there, and if you can use that abstraction, if it works for your use case, it's great. And in my opinion, is something that has worked well for us. We talked about that abstraction of keeping the schema encoding and decoding logic in the apps, or you can put it on the producer consumer library, or you can put it on the server side, which is Kafka or Pulsar brokers or schema registry. With the abstracted model, you have lighter apps, and you can concentrate on whatever you're doing inside the app, following single responsibility principle. Evolution is easy because versioning is supported out of the box with the schema constructs that Kafka and Pulsar provide. Upgrades are easy because there is a maturity that has developed over the years. There is a process that you can follow depending on the use case. You have to decide which process do you like, and you can just follow that. And in our opinion, we have found that going this route means we have had less bugs. If you go for the flexibility where you put your producer consumer on, so if you put your schema encoding and decoding logic in all your producer apps and consumer apps, of course, you have some good things like schema format flexibility, where one app is maybe written in Java, so it can use Java serialization, deserialization. Other one is written in Python, so that app can use Python's pickle. The other one is written in Ruby, so maybe it can use Ruby. Or maybe let's say you are a Java shop inside your organization, right? Every service is written in Java. In that case, maybe it's fine. But if you want to go polyglot from there, where there are some newer people, they want to use Python, and now they'll have problems decoding the data that was produced using Java. Evolution is some of schema, like the newer version of schema, right? In future, you may add a new field, or you may want to delete a field from there. If you want to upgrade your schemas, you have to decide on your versioning logic. That is something you'll have to still manage either in your producer consumer libraries, or you have to manage it on your producing and consuming app, and that too at each of the producing app and each of the consuming apps. And then you have to decide what will be your upgrade path. Will you upgrade your producers first? Will you upgrade your consumers first? Or will you allow for any order and all of them works, right? And in our opinion, we have generally found that this scenario is a little bit buggy and even difficult to debug when there are issues. As far as schemalessness is concerned, the whole schemalessness is something that is good for some use cases, in my opinion, but there is no such thing as schema-less, I think, because if you don't have schema, you can't decode bytes, so you can't get back your record that you wrote. So if you are not going schema full, you're going schema less, it just means that your schema is scattered randomly throughout your code. It is impossible to troubleshoot anything non-trivial because there are a lot of assumptions, and there are no sort of explicit requirements that are documented and can be followed by your future devs. Like if nothing is absolutely best all the time, in my opinion. So flexibility is a good choice only when you have non-uniform data of some form. For instance, you have in your event, you have a field which decides how are you going to decode the rest of the object. Maybe then you want to be flexible and don't want to commit to it for every message on that topic. Maybe you are consuming from some third-party app and you want to leave the representation schema or structure to that third party, and you are just a hop. Then you don't want to fiddle with all the schemas and all. You just get whatever you get from there as bytes and stream those bytes back to maybe somewhere else for processing. And then you want to be away from all the schema handling. And then if you have a case where schema changes happen very frequently, then schema migration can be a pain. So schema flexibility, schema less is what sort of used for that is a good choice. We will now look at different ways of representing schemas. Choice number one is you can use Java's own serialization if you're using Java. You can use Pickle if you're using Python. You can use Partial if you're using Ruby. The good part about it is that you're already familiar with your programming language. You have probably already used the serialization, deserialization in some places in your app already. So you can just use that code. There's nothing new to learn. But if you use Java serialization and deserialization, and you suddenly have some Python apps, you may have problems because you have logged yourself inside Java serialization and deserialization, and the Python's pickle will probably work differently. And then because you are using your own serialization and deserialization, you will also have to think of your own schema evolution path and your order of upgrades among producers and consumers. Choice number two for schema representation is you already have your REST APIs, so you can use something similar where you can represent requests and responses in REST in JSON or XML. Similarly, you can represent your streaming events using the same JSON or XML, so you can share code. There's no learning curve. It's all text, so it is easy to debug. One of the problems is space. So if you look at JSON, if you look at your REST API structures of request and response, every message has the name of the key along with the value. So that key name is the extra data that you're sending with every message. And when you work on a scale, then that is a lot of extra data. So if you want to be space efficient, this may not be a great idea. And so JSON has auto type detection, which can be problematic at types. You have to also think of how are you going to introduce new types. Maybe there are some nested objects. Will you ship a library with all your data transfer objects or your plain old Java objects, Pojo? So will you make a library of all the Pojos and ship around and be included in all the producer apps and all the consumer apps? Maybe you will document all the data types that are supported right now. You have to synchronize it between all the producer apps and all the consumer apps. And maybe on the consumer, you can make a logic where you say, if you see a new field and you in your Pojo don't have that new field, then you just ignore those fields at the time of decoding things. But yeah, I mean, we've tried this and we have actually burnt our hands. What we actually like is struct schema, which is in Pulsar's world, struct schema is the abstraction below which you have Avro's implementation and Thrift's implementation and Proto's implementation. These are all binary formats where the key name is not shipped as part of every message. So binary formats are all space efficient. They have been in use in the streaming ecosystem over the years. So they have matured, they're all well documented, libraries are supported. Converting from Avro or Thrift or Proto to your programming language constructs like Avro file to Java's class file or Java's class file to Avro's native file is pretty easy. There are libraries available in multiple different languages, pretty much all the famous programming languages. So you can just use those and they are sort of pretty stable. And the versioning and upgrade path and all are already defined. One issue that we have had is there is actually a little bit of a learning curve as far as this method is concerned. But in our opinion, I mean, in the use cases that we have used these, we found that this learning curve is absolutely worth it. Now we will look at Apache Pulsar very quickly what it is. And we will also look at some code snippets, some very small code snippets to show how actually schema can be enforced when you write to your stream platform, as in Apache Pulsar or Apache Kafka. So Apache Pulsar, in my own opinion, is the next generation of streaming after Kafka. It's completely cloud native. It's distributed store, and it provides messaging as well as streaming. It has a really nice modular design where there is a stateless layer, which is broker for serving the data. There is storage layer that is separate. You can horizontally scale either compute or store completely independent of each other. There's low latency and high throughput writes because it uses RocksDB, and which implements LSM under the hood. So it takes good advantage of SSDs if you have high throughput with your SSDs. Multi-tenancy is supported off the box. Geo-replication is supported off the box, so you have that extra disaster recovery. Plus, if you want to keep your data close to your consumers, which are distributed across the geography, then Apache Pulsar is a really good streaming platform to have. So we'll first look at programming language own serialization, deserialization, how to do that with Pulsar's constructs. Let's say you have a user which has two attributes, name and age. You make a producer and you say that I want to use just bytes that I give you, just send it over to Pulsar. You make your user object, you supply your name and age, you make your user object using your programming languages, serialization or deserialization like Java Zone, Python Speckle, or Ruby's Marshall, using those serialize this to bytes, and then this message object, you just say, hey producer, send me this byte of message to Pulsar. This is what using byte schema. If you want to use a string schema, you tell your producer that you want to use a string, and you make a new producer. You say schema.string, and then you say, hey producer, send me this new message, which has the value as a string. You can have any structure in this. You can have maybe a JSON serialized string or something, all of that work. And then the consumer knows that this JSON, so it deserializes it. On the consumer side, you again say that I want to use string. You define the schema type, which is schema.string. And then when you receive, you get back your string data. If you use Avro to serialize and deserialize, when you make your producer, you say, you know what, I have this user class. I want to make Avro schema out of it, and my producer should use that Avro schema, which is made here. So this Avro schema is what I want to use when I produce. So encode my data using this schema, and when you make a new message, you make the user object supplying the user name, and then you have user age, and just send it over. On the consumer side, you tell your consumer instance that you want to receive as the user object. You want to use Avro, and the Avro has to be what is built on top of the user class. And then when you receive messages going along on this consumer app, you will keep getting the user objects. So schema registry is something that is supported by Pulsar as well as Kafka. It provides you topic to schema mapping. It stores your schema, and schema can be versioned again. The whole upgrade path and evolution and all of that with different modes of compatibility. When you do schema evolution, all of that as are part of schema registry. Producer, when it produces messages, it adds schema, and it makes the new versions and all. Consumer fetches schema and data from the topic and deserializes it and gives it back to your app to use it. Schema itself, if you look at the structure of it, every schema of course has a name. It has a payload which describes the attributes in the schema. then type, which is could be it could be Avro, it could be Proto, it could be JSON, and then you can have properties, which is just a map of string and string. So any thing that you want to send along. A schema evolution, again, you can use manual evolution, where every time there is a new schema, you actually review that schema and then go ahead and apply that schema on the schema registry. You have the REST API calls, you have the CLI commands and all of that to help you with your manual evaluation process. We have used manual evaluation process for a while, and it sort of works. It's especially good if you have developers where they're not sort of really good with these things. So then it gives you time to sort of, with the code review approach, guide them with schema evolution and new schemas, or using the older schemas only. But you can also use the automated approach. We will discuss more about it going ahead. Basically, what you will do is, on a topic, you will define the kind of compatibility that you want, the sort of amount of strictness that you want as far as the evolution of schema goes. And then depending on the compatibility, you're told your topic, new schemas will be tested against those. If they conform to the rules within that compatibility mode, then they'll be accepted. Otherwise, the new schema will be rejected by the producer. So there are a lot of different compatibility modes. Always compatible mode will always accept your new version of schema. So if you send a new message which has a completely different schema, it will assume that, yeah, you know what, like I'll take this as the new version. Always incompatible is basically you want to disable schema evolution. There is one schema and everybody should just use this schema forever. Backward compatibility is where your current new schema will be checked against the previous schema for backward compatibility. So for instance, you have a new schema, which is, let's say you already had V1 and V2, and the new schema is V3. So V3 will be checked against V2 to make sure that V3 is backward compatible with V2. In this mode, you can add optional fields, you can delete fields, and you have to upgrade your consumer first. Backward transitive is similar to backward, except for the fact that if you have a new schema V3 and V2 and V1 were already there, then V3 will be checked for backward compatibility against V2, and V3 will also be checked for backward compatibility against V1. Forward compatibility, again, is checking for forward compatibility against only V2. Here you can add fields, but you can only delete optional fields, and you have to upgrade your producer first. Forward transitive is where if your new schema version is again V3, it will be checked for forward compatibility against V2 as well as V1. Full compatibility is backward as plus forward, and full transitive is full compatibility checked against all the previous versions. If you look at typical producer workflow, you will have a new piece of data that is coming through. It will meet the producer will go look for the schema information for this topic. So now it will look at your schema and see that is this schema already part of the schema registry for this topic. If it is already there, then it will accept, it will connect the producer, and then you can keep producing data. If this schema was not registered already, then it will check if you have enabled auto update. If auto update is enabled, then it will check for the compatibility mode. Given this compatibility mode, now it will check for it will check if this new schema conforms to the rules imposed by this compatibility strategy, and if this new schema is fine, then against this schema is registered in the schema registry, and you get back a new version of the schema, and then your producer is connected, and you can go happily producing more and more data on top of this new schema. Now, if your update schema is enabled and your compatibility mode tells you that the new schema that you're trying to submit does not conform to the rules of compatibility mode, then your producer will reject the message. And this is actually a good place where we've actually caught a lot of bugs in our apps that seep through and try to produce the wrong data. On the consumer, again, the consumer, when the app, when it comes up, it tries to connect the consumer to the broker. Again, the consumer gets the schema information. It goes ahead, checks if the data that it wants to consume, the schema, the local producer has a local producer and consumer have all been there. If they're all there, then it will check for compatibility strategy, and if everything in the new schema attributes is compatible with the old ones according to the compatibility rules, then it is passed through. Otherwise, it will go and check if your auto update is enabled. If it is enabled, then this new schema that you supplied as part of the consumer definition, we looked at that code previously, that is so that is registered, and then your consumer can now connect again. Otherwise, your consumer cannot connect to the broker. The broker will reject the connection request from the consumer app and throw an error. If you want to use, on the producer side, if you want to use the semantics of Pulsar, the workflow that we just saw in the flow diagram, then when making the producer, you just say schema dot auto produce, and consumer you say schema dot auto consume. So the other learning that we have had over last couple of years using schemas is that you don't always want to bind your topic and schema one-to-one. Rather, we prefer relative ordering. So you would know that all the messages on one topic, or if you are using partition topic, all the messages on one partition are always ordered. So what we do is we keep a domain. In that domain, you may have multiple different types of objects like user, account, and the subscription of that account. And on that topic, we want to evolve all the schemas parallelly. So when you submit user v3, it checks for compatibility only against user v2 and not against account v2. So all the different objects have their own evolution paths. And then if your source and sync apart from the streaming platform itself, like Pulsar has source and sync support with Flink and Spark and Elasticsearch and whatnot. So you can show the same schema across your pipeline if your use case allows for it. If, of course, you decorate your data over Pulsar or some place in your pipeline, then of course your schema changes. Lastly, our own learnings. We think Avro is good. Proto and JSON are good as well, but I think Avro's adoption is something that I've always found good. If you have a lot of data, then you want to be space efficient, so binary representation is good. If your use case allows for it, use the schema management. Only use flexibility if you really need it. Use schema registry by default. I would recommend Avro. It's been good for us, and it's always good to put that extra effort and set the compatibility and evolution path and upgrade path, upgrade order, all of those upfront, and force it for the producers and consumers to follow it. So I've left some references if you want to read more, and then these are my contacts. You can talk to me over LinkedIn. You can see my previous talks on my YouTube playlist, and then my slides, I leave them on my SlideShare account. You can also talk to me on Twitter. So do let me know if you have any questions or if you just want to say hello. Thank you.